Alright, so this will be our proof of diagonals of a parallelogram bisect each other. So here we have our beginning picture, and from the statement, what we can draw as a given is that ABCD is a parallelogram. So remember, always want to start with your givens. ABCD is a parallelogram. Is given to us. Now, when writing a proof, when you start with your givens, you can come right off of that with what you happen to know because of that given. So in this case, we're actually going to make two separate statements. One is that AB is parallel to DC. The other is that AD is parallel to BC. So those two statements are both going to be true because of the definition of a parallelogram. Okay, so at this point it might help us to draw a smaller or a different picture of this that's not quite so cluttered. Because from our plan we know we need to prove that BC and AD are congruent. So I might redraw my picture over here with A, B, C, and D, but only draw in diagonal BD. And what this is going to allow me to do is now I've said that these two sides are parallel and these two sides are parallel. And so I'm going to work with these two larger triangles over here. I know that I've got BD drawn in this picture, so BD is congruent to itself. And that will be our reflexive property. That gives me a congruent side. Now coming back over here to my parallel lines, I'm going to know that because AB is parallel to DC, I'm going to be able to state that ABD is congruent to CDB. Those are alternate interior angles, so that will be my reasoning for that. So angle ABD is congruent to angle CDB. And that's by the alternate interior angles theorem. Similarly, coming off of AD being parallel to BC, we will have the statement that CBD and ADB are congruent. And that's also because they're alternate interior angles between parallel lines, which are congruent. Now I've got in this picture, we now have enough information to say that the two triangles are congruent. So we can bring this statement, and this statement together to say triangle ABD is congruent to triangle, so we want A to B to D, so this one's got to be C to D to B. That's true because of angle, side, angle. All right, now we've got these two sides congruent to each other. We also, from over here, have that ADB is congruent to CBD, this angle up there. I've already got two of the three parts of that other triangle, or set of triangles, to be congruent from these statements. Oh, we need to actually come off of here and say that those two segments are congruent. Now, AD congruent to BC there, and that's going to be a CPCTC. Is corresponding parts of congruent triangles are congruent. So there's that side. Now, as we're working on the problem, we've got to get in another pair of angles. And it's the way we set this up. This didn't help much with the second pair of angles, but I can see in my picture up here, I've got those two angles which are in the vertical angles position. So that's going to come out as a completely separate statement, that angle AED and angle BEC are vertical angles. We're getting that just from the picture, which is why we don't have an arrow coming to it from anywhere. And really, just looking at the picture, we're applying the definition of vertical angles. Now, one of the properties that we can use comes from vertical angles, that vertical angles are congruent. So we can now say that angle AED is congruent to angle AED. Let's go CEB. We'll name it slightly differently so it matches with our triangles later on. And that's the vertical angles property. Okay, so we can mark up our picture here, saying those two angles are also congruent. Now we've got two angles on a side not in between them, congruent between the two triangles. So let's bring those three things together. So here's one angle, here's the side that's not in between them, and then we're doing ADB, that's this one, to come down here. With those three pieces of information, I can say that I have congruent triangles now. The triangle AED is congruent to triangle CEB. And that's two angles and a side not in between them congruency statement. You can also write that as SAA. Now, if two triangles are congruent, then their parts are congruent. And this is where we're going to get to AE being congruent to EC and BE being congruent to ED. And that's going to be almost the end of our proof. So we say AE is congruent to CE. And that reasoning for that is that the corresponding parts of congruent triangles are congruent. And then we can also say that DE is congruent to BE. The same CPCTC all over again. And so now I'm going to pull us back to the picture for a second. We just said that AE is congruent to EC. If those two pieces are congruent, then the line that cuts through that segment and breaks them into two congruent parts is a bisector. So DB is bisecting AC because it cuts it into two congruent parts. Coming off of here, we can now say that DB bisects AC, and my reason for that statement is that I happen to know what the definition of a segment bisector is. And same thing for this, but this is the other pair of sides, or pair bisecting itself. So this will be, we have to write this the other way, because the proof was that they bisect each other, so we actually do have to show that each one bisects the other one. So we know that AC bisects DB. So in this case, DE and BE were the same. It's another definition of segment bisector. Okay. And then we get to wrap up our proof. DB and AC are the diagonals of parallelogram ABCD. So now that I've shown separately that they bisect, I can actually bring them together and make my final statement, and that is that in fact the diagonals of a parallelogram bisect each other. So here's my final statement. This is the thing I was asked to prove, so that's always going to be my last statement, is exactly what I was being asked to prove. And my reason that I'm going to use to support that is that DB and AC are the diagonals of parallelogram ABCD. And so that wraps up my proof.